Morning, everybody. Today's learning objective is transition elements. So first, we have to know the periodic table importance. Periodic table is the most important chemistry reference there. It arranges all the known elements in an informative array. These elements are arranged from left to right and top to bottom in the order of the increasing atomic number. And the order generally coincides with increasing atomic mass. So the periodic table has been arranged into four different. Yeah, it has been arranged into four different blocks. One is the S block element. The left side you can see two groups in the left S block element and P block elements, D block elements, and F block elements. So S, P, D, F. So depending on the valence electron and the orbital, valence electron and the orbital, there is a classification of the elements or blocks. So, you know the left side of the periodic table at the CSP, and in the center you can see the D block elements. At the bottom you can see F block elements. So today we'll discuss about the D block elements in the atomic ground state contains the highest electron in the D orbital from the D block elements. I'm repeating, elements in which the atomic ground state contains highest energy electron in the d orbital are called d block elements. These are otherwise called as the transition elements. Why do you call them as the transition elements? Because these exhibit the transition properties. Here in between the and the p block, these are arranged and having the transition properties. Similarities within a given period and within a given group. The last electrons added are the inner electrons. They, and the outermost are the valence electrons of these enter into the d orbital. So there are 40 such elements with atomic numbers from 20 to 30. Yeah. In the d block elements, we are having 40 elements with atomic numbers from 20 to 30, 39 to 48, 57, and 72 to 80, 89, and 104 to 112, arranged in four periods in the periodic table. D block, and here you can see the D block and the F block elements. So here the white ones 1A and 2A are the S block elements. At 3A, 4A, 5A, 6A, 7A, 8A comes under the D block elements. So in the D block elements, you can see the 3B, 4B, 5B, 6B, 7B, and 8B are the three groups. 1B and 2. All these are the transition elements. And in the transition elements, not according to the groups we have to talk, it is depending upon the periods we have to talk. So it is 3D series, 4D series, 5D series. So the D block elements are known as the transition elements as the line between the S block and the P block. These show transition properties between highly reactive metallic elements, that is S block, which form ionic compounds, and p block elements, which form covalent compounds. So an element whose atom has incomplete d orbitals is called transition element, d block element, or which give rise to the cation with an incomplete d shell are called as the transition elements. So by this definition, zinc, cadmium, mercury are excluded from the transition metals as they have n-1 D10 NS2 configuration. They do not form +2 oxidation state. batteries retain region configuration. Element 1 or 2, even that can be excluded from transition through the oxidation states, unlike the upside. And it has a radioactive nature, 112. And now, so transition which corresponds the elements present from 3 to 11 periods as shown in the period. So here you can see the table. These 3 to 12, these groups, we have to talk around with respect to its 5D series. So the general properties for these transition elements are, these are the silvery metals, exception of the copper. And these are dense with high melting points and boiling points. So these are the general properties. They tend to be hard with high tensile strength and good mechanical properties. They're good conductors of the heat and electricity. These are good conductors of the heat and electricity. And most have the closed packed structure of the atoms. These are much less reactive than the S block elements. Strong forces exist between these separate atoms in the metals, and these are known as the metallic bonds. These elements are known as the metallic bonds. Yeah, this can be explained by the movement of the outer shell electrons of the metal as are randomly throughout the lattice of the regularly spaced positive ions. The moving electrons are referred to as sea of electrons in these metals. Here, and coming to the next properties, these are the sea of electrons. Each positively charged ion is attracted to sea of electrons and vice versa. These electrostatic attractions bind the structure together, and when force is applied to the metal, the layers of the atoms slide over one another, slipping. So, and this is why the metals can be hammered into different shapes. They have the malleable property and even the ductile property. For alloys, different sized atoms interact generally on the orderly arrangement of the atoms. Okay, so transition elements have certain characteristic properties which can be discussed. That is the form compounds with wide variety of the oxidation states. In the next slide, we'll discuss it. And they're having different color properties. They form complex compounds. They act as a good catalysts. They show different magnetic behavior. Example, iron, cobalt, and nickel are ferromagnetic. Copper, it is diamagnetic. And platinum, it is the temperature independent paramagnetic. Now coming to the electronic configurations. Here, these are the ones which I have showing you separately. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. 3D series elements. In the d block elements, the electrons are added to the penultimate shell because the outer ns orbital in the d block elements are of low energy than the n-1 d orbitals. In coming to the fourth period, the elements with atomic numbers from 21 to 29, scandium to copper, they have 2 electrons in their outermost valence orbitals. Here, copper is an exception and chromium is an exception. Generally, the electronic configuration of from the scandium, titanium, zinc, 2 are having the orgone configuration, and 3D 1 to 10 and 4 is 2 is the general electronic configuration. So similarly for the second transition series, that is 4D series, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. There you are having the electronic configuration, orgon configuration 3D1 and 5s1, 5s2. Sorry, krypton configuration 3D1 to 10. Sorry, 4D. This is 4D series and 4D 1 to 10 and 5s. 5s 0 or 1 or 2. 0 to 2. I'm repeating the electronic configuration for 4D series. It is the general krypton configuration and 4D1 to 4D1 to 10 and 5s 0 to 2. Now coming to the third transition series, that is 5D series. 60 is almost incomplete. Thus lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury. The configurations are xenon configuration and 5D1 to 5D10 and 6s2 or 6s2 or 1. Okay, I'm repeating. So here, almost in the 5D series, from hafnium, they are entering into 4f orbitals. Yeah, these are entering into the 4f series. Okay, in the first series, that is 3D series, scandium and through copper, the differentiating electrons into 3D orbital. Irregularities are observed at chromium and copper. Exceptions occur everywhere. In the second transition series, yttrium through silver differentiating electrons into 4D series, almost there are more irregularities. The irregularity of the configurations with respect to molybdenum and silver. They just like chromium, the molybdenum and the silver, and which can be explained based on the stability in halfly full and fully full shells. And coming to the niobium, skips with the palladium's the difference. The palladium, which has 4D10 and 5s0 instead of 4D8 and 5s2, can be attributed to the electron collisions and nuclear electron attractions. Here. Now, in the third transition series, as I've told you, they've entered into the F-block elements. In third, lanthanum, La, to mercury, differentiating electrons into 5D series. The 14 elements between lanthanum and hafnium involve filling of them from hafnium to here. From hafnium, the 14 elements. Hafnium involves the 4f series, 4f orbitals and are called as the inner transitions, and these do not belong to the series. The 14 elements between the lanthanum and hafnium, they are having involvement of the 4f orbitals, and these are called as the inner transition elements and do not belong to the series. That is, they don't belong to the 5D series. They are entering into the inner transition elements, that is the F-block elements. Fourth, here, as I've told you, in fourth transition series, in the fourth transition series, inner from actinium, from here you can see here, actinium to unbium, Anandiyam. The differentiating electron enters the 6p subshell. In this series, irregularity is dermostadium and which has lanthanum instead of Rn. So there are irregularities. The electronic configuration of the transition elements depends upon several factors. It depends on the several factors: electron-electron repulsions, nuclear electron attractions, shielding electron, and the nuclear interaction by exchange energies. And when orbitals are empty, 4f orbital is lower in energy than 3d series. So thus transition elements, the s electrons are first removed, then come to the d electrons. Coming to the atomic size and atomic radius. Coming to the atomic size and atomic radii. Radii in a given transition decreases progressively on moving from left to right of the periods. In transition elements, the differentiating electrons enters the same d orbital while the nuclear charge increases by 1. Nuclear charge increases by 1. And coming from this transition elements, the differentiating electron enters the same d orbital which the nuclear charge increases by 1. The increased nuclear charge attracts the increased, whatever you see, the increased nuclear charge attracts the electron cloud more effectively, causing the size difference, contraction. Decrease in the volume. Decrease in the radii across the period is not uniform. The decrease is very small when compared to the decrease in the S and P block. Compared to the S and P block, the decrease is very less. The decrease is very less in S and P block elements. Atomic radii, it's almost close due to the screening effect of the nuclear attraction in the electrons added, and two opposing for effects, the atomic radii do not alter much from chromium to copper. Yeah, ionic radii also the same trends, just like the atomic radii. Decreases with increase in the atomic. Ionic radii decreases with increase in the atomic number due to increase in nuclear charge. Here you can see the different elements. It's how they are, you can see scandium. They are available. Scandium, vanadium, manganese, iron, cobalt, nickel, copper. Next, coming to the orbital occupancy, we'll see orbital diagram, partial orbital diagram. Here I have told you scandium, which is here the electron you can see 4s to 3d1. 2 s electrons and in D you are having 1 and 2. Almost all the elements from scandium to, you can see from scandium to titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. You're having almost all the elements, you're having 4s2 electrons. But in copper and chromium and copper, you're having single electrons. You can see here, yeah, 3d1, 3d2, 3d3, 3d5, 3d5, yeah, 3d6 in iron, and here 3d7, and this is 3d8, 3d9. Yeah, it's almost 1 is extra. It's 3d9, 1 electron is extra. Yeah, this is 3d10. And the unpaired electrons you can see by counting how they are changed. Maximum of 5 unpaired electrons. And then again it decreases. Now, what are the horizontal trends? Atomic radius, electronegativity, fast ionization. As I have told you, atomic radii, how it's going on. Once if you see the atomic radii, in general, the atomic radii in a given transition will decrease progressively, coming from left to right. Okay? Coming from left to right, it's decreasing progressively from left to right in a period. The differentiating electrons into the same orbit of where the nuclear charge is increasing. The increased nuclear charge attracts the electron cloud effectively, causing contraction in size. The decrease in the radii across a period is not unique. The decrease is very small compared to the decrease in s block elements. The atomic radii of the elements from chromium to copper are very close. From chromium to copper, it is almost close. Till here. Once if you see from scandium to zinc. Yeah, these are our elements. Scandium to zinc. Now, this is about the atomic radius and at ionic group and similarly ionic group. And now coming to the ionization potential, you can see the electronegativities very clearly depicted. How the electronegativity is increasing. The radius here, it is decreasing 162, 147, 34, 128, 27, 26. It's almost decreasing atomic radius, we have discussed. And coming to the electronegativity from scandium, it's increasing. As the nuclear attraction is more, the electronegativity is 1.3, 1.5, 1.6, 1.6, 1.5, 1.8, 1.8. Here, almost same 1.8, 1.9. But for zinc, it is decreasing. Why this happens is it's almost filled electrons. Electronegativity is decreasing. Now coming to the first ionization energy. Coming to the first ionization energy. Scandium, here you can see 631, titanium 658, vanadium 650. So first ionization energy is increasing. Why? Because the electronegativity is increasing. As this electronegativity increased, ionization energy also increases. 631, 658, 650, 653, 770. So only here you can observe, just here 53. Almost it's increasing. Only for titanium it's somewhat different, but scandium slowly it's increasing. The first ionization energy. What is first ionization energy? Energy required to remove the outermost valence electron. First valence electron. Now we'll see the oxidation states. That's a very peculiar property. A variable property has a variable oxidation states. Scandium, it exhibits here. What is oxidation state? Oxidation state exhibiting the variable oxidation is an important property of transition elements. A successive ionization energy at the gradually decrease when is removed. So here on removal of electron you get the positive charge, or the charge exhibited on an atom is nothing but the oxidation state. And in this one you are having different oxidation states. 0, +1, +2, +3, +4, +5, +6, and +7. These are the different oxidation states exhibited by the atoms. So D block means. See the 3D series +1 oxidation state. Vanadium exhibits +1, chromium, manganese, cobalt, nickel, copper exhibit +1. Here the D configuration is also written. Coming to the +2, titanium +2, vanadium +2, chromium +2, manganese +2, iron also exhibits +2, cobalt, nickel, copper, zinc. And coming to +3 oxidation state, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper. All these exhibit +3 oxidation state. Coming to the +4 oxidation state. +4 it is exhibited by titanium, vanadium, chromium, manganese, iron, cobalt, and nickel. And the D configurations are also written. Coming to the +5 oxidation state, by losing 5 electrons, you get +5. How you get the plus oxidation? By losing of electrons. So you get +5 in vanadium, chromium, manganese, and nickel. Similarly, chromium oxidation 6+6 is exhibited in chromium, manganese, and iron. And coming to the +7 oxidation state, which is exhibited by manganese. So number of oxidation states are exhibited by manganese. 0, 2, +7. So these are the different oxidation states observed. Oxidation states of first row transition elements given in the table 1.3. What explains here this? What I'm telling this 23.2 table. There is a relationship between the outer electronic configuration of the transition elements and outer transition elements, as well as various possible oxidation states. Many elements exhibit oxidation state. Many elements exhibit oxidation state, and which differ from each other in value. Most oxidation states for each element include +2, +3, or both +3 and relatively more common at the beginning of the series. So you can see, and +2 is more common. Most of the elements exhibit the +2 oxidation states. And up to manganese, there is decrease in the number of oxidation states. Okay. So scandium, titanium, vanadium, chromium, manganese display the maximum oxidation states. Scandium, titanium, vanadium, chromium, and manganese exhibit maximum oxidation states. You can observe. So this is about the variable oxidation states, variable oxidation states of the elements, transition elements. Coming to the standard electrode potentials, if lower is the oxidation state, more is the metallic nature. Metals have tendency to lose electrons and convert into positive charge. These go into the solution and when placed in the water, or a solution is containing its own ions, the magnitude of the electrode potential set up between two depends upon the nature of the metal and the number of electrons involved, the activity of the ions in the solution of the liquid can be given by the expression. Okay, E is equal to E naught plus RT by NF ln 1 by activity of the metal. Using that we can do. So the redox potentials can, I know, and in here the in general the redox couples are written oxidation reduction redox, oxidation form and a reduction form. So the redox potential, why, how they are affecting the redox potentials, how they are affecting the sublimation energy of the solid metal, ionization energy of the gaseous metal, hydration energy of the gaseous ion. So the redox potential for different elements can be given in odd values. So titanium it is minus 1.3. Scandium it is minus 2.03. Titanium it is minus 1.11. Sorry, minus 1.63. Vanadium it is, as I've told you, the redox potential how they're getting affected by sublimation energy, ionization energy, hydration energy. Okay, so the metal ions, how they lose electron, convert to positive ions, they go into the solution placed in water and containing its own ions. Thereby they exhibit some potential. Scandium it is minus 2.08, not given. Titanium it is minus 1.63. Vanadium it is minus 1.19 or 18. And chromium it is 0.91 to 94. Manganese it is minus 1.18. Iron it is 0.44. Cobalt it is minus 0.28. Nickel it is minus 0.25. And copper it is 0.34 plus. And for zinc it is minus 0.76. These are the standard reduction potentials for all the transition elements except of the carbon mercury, lower negative than that of the hydrogen, taken as zero. Mercury not given here, but copper in this series can be. Some elements involve the metals involve the hydrogen very slowly and they protect from the attack of the acids by the thin previous layer of the inert oxide. Next, you can see the colors. They exhibit different colors, this transition elements. So why do we observe these colors? The reason for these colors, why only these transition elements observed, we can observe the color properly. The compounds of the D blockings are colored in the solid state and in the solution state. Electrons in the partially filled D subshell absorbs visible light or move towards slightly higher energy d orbital. They exhibit different colors. The color of the ion depends upon the ligand bonded to the metals. Copper, hydrogen copper, you get pale blue and then changes to dark green bills of iron and even to green if there are sufficient chloride ions. Cobalt chloride is there. That's it. The color of the transition elements depends upon the presence of the air due to unpaired electrons. Presence of the d electrons in the transition metal atom. Arrangement of the ligands around the ion and nature of the ligand. So the color of the transition which depends upon these three properties. That's the chromate and the dichromate. We get yellow color. Dichromate will be orange. This is a chromate. Chromium with oxygens 4. Here, 2 chromiums and 7 oxygens. Yellow color, orange color. It's all due to the unpaired electrons, arrangement of the ligands around the elements, and nature of the ligands. And valence state electronegativity. See, electron pulling nature is the electron. The metal in the higher oxidation states, they're more positive. They have strong pull on the electrons. Then it's more electron. Yes, effective electronegativity. Previously, as I've discussed oxidation states of the manganese, here some of the oxidation states. The oxidation state and the example in the space. How the resistance is increasing with respect to this oxidation states. Manganese plus 2 D5 configuration basically achieve blue. MnO3 plus 3 oxidation state P4. Basically achieve. Manganese dioxide Mn itself plus 4 state here. Manganese dioxide MnO2 D3 configuration and manganese oxide here D1 and M6 oxidation state. 7 oxidation state this manganese oxide D0 and acidic nature. This is how when with respect to the acidic nature they keep changing. I hope everybody have understood my class. What we have discussed in today's class is about the transition elements. So the periodic table, most important chemistry reference there, arranges all elements, known elements in an informative way. From left to right, top to bottom, increasing the elements. Such we are having 4 blocks. Depending upon the valence electron entering into the valence shell, we have 4 blocks: S block, P block, D block, and in between S and P are having this D block elements. These are otherwise called as transition elements. They have different transition properties, oxidation states, different oxidation states, electrode potential, complex nature, catalyst, complex formation, catalyst, color, alloy formation. All these are the variable properties exhibited only by transition elements. Here we have seen about the atomic gradient. We have seen the configurations, orbital occupancy, the electronegative trends, and ionization energy, how it's increasing. We have seen in 3D series. And we have discussed about the multiple oxidation states, and the behavior of the and reducing strength and the metallic behavior. The color properties are also discussed. Even the magnetic properties, it is due to unpaired electrons. Okay. Here are the color properties, different compounds. The valence state, electronegativity nature, and the oxidation state, and how the acidity, basicity are increasing. Have discussed. Thank you, everybody. You understood the class.